Hi there everyone, welcome to the MCAT ACE lecture for the General Chemistry series, and in today's lecture we are going to be covering intermolecular forces, and sometimes this is abbreviated as IMF. You may also hear this term referred to as interparticle forces. However, it is all referencing the same material when you're looking at it from a general chemistry perspective. So let's go ahead and take a look at the overview here in terms of what we would hope to cover in this lecture, and then we'll go ahead and get started on some of the material. So the first thing we need to discuss in some brief detail is we need to define what intermolecular forces are, and part of doing that is we're going to want to compare intermolecular forces to intramolecular forces, because there is a difference between an intermolecular force and an intramolecular force, where the intra is talking about bonds between atoms, and the inter is talking about some sort of activity between two molecules, not just the atoms within a molecule. So then we'll discuss the effects of physical properties. So in other words, the effects that intermolecular forces are going to play on physical properties of a substance. Things like melting point, boiling point, so on. We're then going to take a look at the various types of intermolecular forces, starting with the weakest, which is known as London dispersion forces. You can see in parentheses here I have van der Waals forces. They do go by several different names. Sometimes it's just London forces, dispersion forces, London dispersion forces, van der Waals forces. They're all the same things. This is a type of temporary dipole. So we're going to take a look at how these temporary dipoles come into being and why they're so weak, because as the name would imply, they're temporary. They're going to be fleeting. They're not going to be around for a very long time. And then we have dipole-dipole forces. So unlike temporary dipoles, you can get permanent dipoles in a molecule when you have a large separation in electronegativity. And when you start to get dipole-dipole forces, these are going to be stronger because they're not a fleeting force. They're going to stay and reside within the molecule, and therefore these dipole forces have quite a strong effect on one another. And electronegativity is what's really going to play into this. So we want to take a brief look at, or remind ourselves about, electronegativity values and how they are going to affect the polarity of a bond, and therefore how bonds within molecules would interact within bonds of other molecules. We'll take a look at hydrogen bonding. Some people have a misconception that hydrogen bonding is its own intermolecular force aside from dipole-dipole forces. There's some truth in that. However, hydrogen bonding is simply the most extreme version of a dipole-dipole force. So it is the highest on the chart in terms of dipole-dipole strength. And because it's so strong, it's only in a select few set of electronegative atoms, we tend to refer to it as hydrogen bonding instead of just a dipole-dipole force. And it gets its own sort of lecture or mini-series most of the time when you're going through a chemistry course. And then finally we'll wrap up with the strongest of the bunch, which is ionic dipole forces. So you can think of ionic dipole forces as something like when you put sodium chloride, which is table salt, into water, and the sodium chloride will dissociate into Na plus and Cl minus ions. Those ionic characters, whether you call them electrolytes, anions, cations, they are going to interact with the water. That's part of why they dissolve so well, and you can take a look at the solubility with that. So those are the topics we're really going to look at and cover, and then of course we'll have a few review questions just to make sure you guys are on the right track. So let's go ahead and get started. And to start, we are going to take a look at the difference between intermolecular forces and intramolecular forces. Now, these terms are so similar that it's easy to get them confused. So what you really want to look at here is the prefix. And when you're looking at the prefix, it's specifically the inter versus intra portion that you are going to want to take a look at here. So we're talking about inter versus intra. And the difference between these two is what they actually mean. So inter means between molecules, whereas intra means within the same molecule. Now, one of the techniques I used to use when I was studying this stuff at first, because I found it confusing, was inter I think of internet. Everybody uses the internet nowadays. You're probably watching this on the internet. So if you are dealing with internet, that is a resource that lets people, similar to molecules, communicate between one another. So think about molecules, whether I have two water molecules or two people, okay? The inter means the ability to connect to another one of your type. So here is a water, and in this case it would be hydrogen bonding with another water. Okay, so this dot here represents the intermolecular force. It's between one water and another water, just like the internet. If I email somebody, it's between one person and another person, right? Then if we look at intra, intra means within the molecule. So when I have H2O, the intramolecular forces are these covalent bonds that exist between the oxygen and the hydrogens. Okay, so I don't have quite as catchy a term for intra, but inter should help you remember in between. But intra, if you were looking at an individual person, it means within that person. So all of my appendages, any bones that are connected, if I'm looking within myself, those would all be an intra-connected network. There is such a thing as intranet, when companies would use something like this in order to communicate internally, but they would not use it to communicate outside of the company itself. So those are the main differences between intermolecular forces and intramolecular forces. So attractive forces between molecules will be inter. That's what this video is going to focus on. And intramolecular forces are going to be the attractive forces between atoms within a molecule. And again, the word that you should kind of trigger here when you see this is we're talking about bonds. All right, so the forces that hold, or the glue that holds these atoms together, those are the intramolecular forces. Those are bonds, covalent bonds primarily when we're looking at these types of subjects, but ionic bonds as well. You could have that ionic static type of behavior, but it's holding the molecule together within the molecule. You're not talking about two molecules communicating with one another. All right, so hopefully that's clear in terms of the difference. Now, what are some of the expected effects that this is going to have when we increase in strength? So remember, I'm going to come back up here for a second, we said that the London dispersion forces are going to be the weakest, and then we increase from there. So dipole-dipole forces, hydrogen bonding, and then finally the ionic dipole forces are going to be the greatest. So what do I expect in terms of physical property? Well, when I look at physical properties and I look at the increasing strength of the molecular forces, I usually see a trend that increases in any of the physical properties. So what do I mean by this? Well, if we have an increase in the strength of the intermolecular force, so I'm going to abbreviate here, IMF. Okay, so an increase in the IMF strength, meaning let's say that I'm comparing one thing that just has the London forces to another one that has hydrogen bonding. What do I expect in terms of comparing their physical properties? Well, an increase in the intermolecular force strength is going to lead to an increase in the physical properties. Okay? So what I mean by this is, think about physical properties. Melting point and boiling point are two that stand out that most students tend to jump towards. If I consider something that only has London forces, so for instance, octane, right? I have to count here, 1, 2, 3, 4, 5, 6, 7, 8. That should be right. 1, 2, 3, 4, 5, 6, 7, 8. Yep. So octane is a hydrocarbon, okay, in various forms. Sometimes you get octanol and things like that. But octane, people might have heard of high octane fuel or things of that nature. You're talking about a hydrocarbon fuel, primarily in gasoline and other fuels like that. And then if you compare water, I would expect the properties of water to be higher in terms of their physical properties. All right? This might be even more evident if you have something like butane. So butane is a gas. You can think of, now sometimes it's condensed. You can think of butane or propane in those canisters that you would buy. They're under pressure, and that's going to change them into the liquid form when you play around with the pressure like that. But propane, butane, all of these hydrocarbons, they're a gas at room temperature, whereas water is a liquid. So what I'm saying is that water has an increased boiling point in comparison to these other compounds. Okay? And I would expect the same thing for alcohols, because they could hydrogen bond, and other groups like that. All right. So before we get into too much comparison of London forces versus, hydrogen bonding and things like that, what we really want to sort of drive home here is that the physical properties, and we can list a couple here, the boiling point, the melting point, okay, etc. So any of those physical properties, viscosity, how slow something will flow, the more the stronger the intermolecular forces, the more intermolecular forces you have, the slower it's going to pour, or the higher the viscosity is going to be. So all of those physical properties tend to increase, and that's simply because I have to put in more energy in order to break up the intermolecular forces. So if the intermolecular force strength is high, it's going to require energy in order to break them apart. So think about a bunch of water molecules that are hanging out together. If I want to take them from a liquid phase where they're closely packed together into a gas phase where they're starting to be further and further apart from one another, I'm going to require energy in order to disperse or break apart these forces that are holding the water molecules together. And that's why we see an increase in boiling point, melting point, etc., is because we have to increase the energy input to break these intermolecular forces apart and start getting the free-flowing molecules when we transition from state to state. We always think solid is the most compact. Then liquid is still very compact, but it's a little more fluid. That's where the term comes from. The atoms can kind of go over top of one another. They're not as rigid. And then in a gas, they're very, very far apart, so much so that they're just going to spread to occupy the volume of the container. So the intermolecular force strength, as it increases, so will the physical properties when we're taking a look at them. All right, so let's take a look at some of the actual intermolecular forces. So the first one that we wanted to cover here is the London dispersion force, again, otherwise known as the van der Waals forces. So in order to make this point, we're going to come up with a molecule that does not have any difference in electronegativity when I look at its bonds. So a good example would be hydrogen. Hydrogen has an electronegativity value of about 2.1. So if I have a 2.1 and a 2.1 and I subtract them, I get 0. So this is nulled out. There is no dipole, or there is no net flow of electrons in one direction here. In other words, even though each individual hydrogen has an electronegativity value associated with it, these are equal pulling partners in the tug of war for these covalent electrons. And so since there's going to be an equal pull in both directions, that means that I'm not going to expect a permanent dipole of any sort here where I could assign and say, hey, this hydrogen is partially positive and the other is partially negative. That wouldn't make any sense because they are both equal when we look at their electronegativity. Now, in order to understand London forces or dispersion forces, you have to understand how bonds work. And this can be very confusing for a lot of students. And that's because when we tend to draw bonds, we show them as this static line here. Okay, so static, when I say static, I'm talking about something that's not in motion, it's not moving. We just draw it on a piece of paper. We say, hey, see this line? It links these two atoms together and they just stay there. They hang out, and that's their bond. They share those electrons together, almost like, you know, my brother and I are holding a piece of rope and we're just standing there and we're not doing anything. But in reality, that's not how electrons work. They don't stay in a static position between these atoms. What you have is the hydrogen with a 1s shell. You have another hydrogen with a 1s shell, and they each have one electron that they bring to the partnership as we start to approach and get involved in this covalent bond. Once these two electrons are close enough together, they are going to be in constant motion. Electrons don't pause and hang out for any given period of time. They are constantly in motion, which means that statistically, at any point in time, I could find the electrons heavier over here, meaning that the two electrons might spend more time over here. They might be completely between the two and look like in a snapshot that they would be static, or they could be over with this hydrogen. So what's happening? Well, what's happening is at time 1, meaning I take a snapshot in time, I look at the hydrogen-hydrogen electron distribution, and these two electrons are found more on the hydrogen on the right. So I put that negative, and I put this as a positive. Okay, so that's at time 1. The electrons are found around this hydrogen here. That's where the electrons are located. And then at time 2, I take another random snapshot. I find that the electrons are now over here because they're constantly traveling. They're now over on the left hydrogen, and this one looks like this. So this is where we come to the idea of a temporary dipole, because we do not have static electrons and electrons are always in motion. They are being moved back and forth between the two hydrogens, sort of in this turbulent, chaotic environment. Now, if I were to take all the snapshots and average them, I would see that it looks a little bit more like this. So sometimes they have these nice bubble-looking maps with different colors, and the red color means that you've got a lot of electron density, and the blue or the green colors, they tend to mean that you don't have as much electron density in that area. And then you look at something like a hydrogen-hydrogen, and it looks like it's just perfectly equally distributed over the two hydrogens. Well, that is true. Okay, that is true. So the best example that I can give you when we're looking at something like this, imagine that I have a card collection. Again, I'm going to go back to if I'm talking about I have a sibling and we have a card collection, right? And the collection is only made up of 2 cards. I have 1 card, and my brother has the other card. And so what we do is we say, look, we really want a complete set of cards. That's the only way that we're really going to feel satisfied. Okay, so what I'm referring to there is the octet rule, the noble gases, right? They have the complete electron set, the total set. So imagine if my brother and I each have 1 card in the set, and we can't seem to find the other one. We come together and we say, hey, look, we'd like to share these so we can say we have a complete set, because that's what's cool. That's the stable thing. That's the thing on the block. Right? So what happens is my brother gives me the card and he says, why don't you hold on to them today and you can go around and show them off to your friends and say you have a complete set. I'll take them tomorrow and you'll give me your card as well as my card back, and then I'll show them off to my friends and we can say that we have a complete set. And we trade off in this behavior every other day, right? So if you were to come and find one of us on one of those days, one of us is going to look like we don't have anything in the collection. The other one's going to look like they have a full collection. And then you come the next day at another snapshot at time 2, and it looks like the other brother has the entire collection, and the one that had it the day before doesn't have anything. So what's going on? Well, if you average it out, you take it out, 50% of the time one brother has the card collection, the other 50% of the time the other brother has the card collection. So you can kind of think of these electrons like a complete set, and the hydrogens are batting them back and forth. They're both taking time with them in order to show off that they have their complete outer shell filled. And so that's what's going on here. Now, why are these such weak forces with one another? So in other words, I could turn around and I could say, hey, look, I've got a hydrogen-hydrogen, and at this particular moment, it looks like this. So the one on the right has all the electron density gathered in its favor, and it bumps into another hydrogen on the street, right? So here's this hydrogen, and this hydrogen is partially positive and it's partially negative on the right. So these are 2 similar ones, right, at a given time. For a very brief moment, there can be an interaction between the partially negative, which has some electrons, and the partially positive, right? So imagine this hydrogen down here, going back to the card collection example, right? This guy, it's his day with the cards. It's his day with the electrons. And so he comes over to this hydrogen and says, hey, look, you don't have anything, so why don't you take a look at my collection and you can be around it, admire it, but I have to give it back tomorrow. So that's why this is temporary, because these are going to disappear. This is a temporary dipole, because it is going to vanish almost as soon as it's there, because the electrons, we're talking on a scale of days when we're using the example of sharing the cards. Electrons don't hang around for days. They're hanging around for split fractions of a second and they're gone. They're already over in some other area. So what's happening is we're constantly forming these new intermolecular attractive forces, and as soon as they're there, they're almost gone. So what happens is the larger a molecule is, the more of these London dispersion forces it can have, because any two atoms that are involved in a bond can have this type of behavior. They can have a moving or a back and forth of the electrons that are involved in the bond. So London dispersion forces are the weakest, but they are also the most common because any single molecule can pull off London dispersion forces. It's not that hard in order to get London dispersion forces because electrons are always moving. So you can get patches where there's some electron density, and then in the similar molecule there's a lack of electron density. They pair up for a brief moment and poof, it's gone. It doesn't hang around. So that is van der Waals / London dispersion forces. All right, temporary, fleeting, they're gone. And I know I was using hydrogen here, but just keep in mind this is still going to apply if you have something like fluorine and fluorine. Just because fluorine is the highest on the electronegativity scale, it's again a 4.0 minus a 4.0. You don't have any type of pull. And so these are equally matched partners. I would expect the same exact thing here, where at one moment I'm going to see, oops, I'm going to see this. That's a negative sign over there. And then at the very next moment, it's going to be distributed like this. So I take the average overall. It's going to look like they're equally shared, because that is what they are. They're equally shared electrons over a long period of time, statistically speaking. All right, so remember, every single molecule that you can come up with, as long as it's a valid Lewis structure, is going to have these temporary dipoles, these London dispersion forces. It is the weakest because it is constantly shifting. It's constantly moving around. All right, so the next thing we're going to talk about is the dipole-dipole forces. So what happens if I have a more permanent dipole, one that's not fleeting quite as much? Now remember, when we started talking about polar dipoles that have a little more permanence, we were talking about when I look at the difference between electronegativities in a bond, I'm looking for 0.4 or above, and then I would start to cut that off maybe around 2.0, because then I'm getting a bit ionic when I'm looking at the differences. So a good example here would be if I have, let's say, a oxygen-nitrogen bond. So if I have a bond between nitrogen and oxygen, at this point I am going to say, well, the oxygen is more electronegative than the nitrogen is. So I would expect this type of relationship to occur in this bond. And when I have something like this, there's going to be a more permanent dipole. And so this is known as the dipole-dipole force. This is a step up from the London dispersion forces because these dipoles do not go away after a given period of time. They are going to be more permanent, and therefore once they align themselves, they don't need to break apart the same way that the temporary dipoles did, because they're not fleeting. They don't move around the same way. They're sort of stuck in that position. So I'm showing you a nitrogen-oxygen bond, but let's use an actual molecule. So here, most people are familiar with hydrochloric acid. Right? Hydrochloric acid, chlorine, and again, this is going to depend on the chart you use. Chlorine usually has around a 3.5 for its electronegativity, and you have about a 2.1 for your hydrogen. So if I look at the difference here, this is getting impressive. We've got a 1.4. So remember, 0.4 means, or below, means we're not really that polar to create a dipole moment. And then anything from 0.4 up to 2.0 is going to be looking somewhere in the range of an escalating polar covalent bond. So we most definitely have a partial negative associated with this chlorine, because the chlorine is the 3.5. The hydrogen, which is a 2.1, is partially positive. And we are not going to see much shifting in this. So in other words, I wouldn't expect the same switch where all of a sudden the hydrogen is going to be more partially negative and the chlorine is going to be more partially positive. The chlorine will always have more in the set in terms of the shared electrons. And that's because we're no longer dealing with equal pulling power. We're saying that one opponent, the chlorine, has the clear advantage in the ability to pull electrons towards itself. So it permanently resides as this partial negative here. So what happens is, if this HCl gets in close proximity to another HCl, there can be a force set up between the partially positive hydrogen and the partially negative chlorine of this second group here. And you can continue to draw a bunch of these. So I could say, all right, now I've got another one down here, and then I've got another one. Wait a minute. Let's back up. I'm starting to draw covalent bonds in between there. That's not a good thing. All right. Okay, so then we've got this guy here. Okay, so this would be partially positive. This would be partially negative. Notice that this chlorine up here could coordinate with this partial positive. So this is what would actually happen in solution. You're going to have these partial positives and partial negatives coordinating with one another. And you can see why this one's going to be a stronger force, because these HCl's aren't going to necessarily break apart their intermolecular forces because of a shift in the electron density, like we were dealing with for the London dispersion forces. So here, we take a look at this and we say, well, if I'm looking at this molecule and then this one and this one, the way they're set up, it's almost like an internet, right? The net, or the spider web being woven here, are these intermolecular forces between the molecules, and these this set sticks, right? These stick. So in other words, these are not temporary. They're not going to go away. All right, so we know electronegativity plays an effect here. Now, one thing we mentioned is hydrogen bonding is a special form of dipole-dipole bonding. So what you want to do when you're thinking about hydrogen bonding is you want to recall the most electronegative element. And we've already discussed it in this lecture here, but just as a reminder for people, fluorine is going to be the highest in the set. And that is followed by oxygen and by nitrogen. So the general trend across the periodic table, if I were to draw a very hand-sketched periodic table, the general trend goes this way, okay, and then it cuts off at the noble gases. So the noble gases are excluded, and then fluorine here is going to be the highest in terms of the electronegativity. And so then we have oxygen and we have nitrogen. Chlorine is also high. And so this bundle over here, okay, that's on the upper right-hand side of the table, excluding the noble gases, that's the most electronegative. So it turns out when you have an oxygen, nitrogen, or fluorine that is involved with a hydrogen, you will get hydrogen bonding. And all this means is that you have a very extreme dipole-dipole force. So the oxygen is very electronegative in comparison to the hydrogen. And so these, just like a regular dipole-dipole force, are going to interact with one another. All we're saying for the hydrogen bonding is that these intermolecular forces are going to be very strong in comparison to other dipole-dipoles. Now, a lot of students say, well, hydrogen's a 2.1. There's things that are lower than hydrogen. What happens if you start getting sodium or things like that as we move down the table, right? Because here's hydrogen, and then here's sodium. So again, remember, and then up here you're going to have lithium. So remember that hydrogen has a 2.1. It tends to act different than the metals. Lithium and sodium, you start getting down into the ones. So you can have like a 1.9, a 1.7, things like that as you're going down. And as you drop off in that direction, in fact, these might even be a little high or generous for this. As you start dropping off in that direction, you're going to get ionic bonds. You're going to start getting salts when you're dealing with that. All right, so we're really dealing with polar covalent bonds when we're talking about this here. So very strong. The hydrogen bonding is very, very strong. And this tends to be a big subject, especially when you're dealing with biochemistry or other things you might come across for MCATs, because there are so many nitrogens and oxygens present in many of the living systems that we have. So molecules, the pathways those molecules go through, certainly water itself is essential for life. There's a lot of hydrogen bonding that is going on when we're dealing with most of the biochemistry molecules that we see on an everyday basis, whether it be DNA or the amino acids or things of that nature. Very, very prevalent. So hydrogen bonding is important. Again, it's really a glorified dipole-dipole force. However, it's still important to realize hydrogen bonding has its own name because it's a step up from the others in terms of how strong these attractions are. And one other note I want to mention here. I know they picked out this name, and honestly, I'm not the biggest fan of this name. Hydrogen bonding, I always have to remind students, when we talk about intermolecular forces are not bonds in the sense of they are not covalent bonds or ionic bonds. So hydrogen bonding, the term, is a little misleading because it's really these attractive forces between molecules. It's not an actual bond. So hydrogen bonding, right, is the upper level of the dipole-dipoles. So you could find other examples, for instance, ethanol, which is drinking alcohol. If I have something like ethanol, the OH here is going to be partially negative, the H here is partially positive, and so that could coordinate, because you have OH bonds, that could coordinate with another ethanol molecule. So again, anything that has NH, OH, or FH bonds, and FH is relatively limited because F is only going to form one bond, so you're talking about hydrofluoric acid, all right? The alcohols and the water molecules are certainly a wide-ranging set of substances. And then when you have nitrogen, you're dealing with a lot of your amines, your amides. Again, you can take a look at some of the nucleotides. You can take a look at some of the amino acids. Carbohydrates would have oxygens in them, and alcohols. So anytime you're dealing with a lot of these biomolecules, there's hydrogen bonding involved. So kind of stressing on this point a little bit more than I am just the regular dipole-dipole forces, because it comes up so often, especially when you're dealing with the types of topics you might find for the MCAT. All right, so the last grouping that we have is that of the ionic dipole. So I am going to stick with water because it's one of the more common examples that you'll come across. So what happens when I have, for instance, sodium chloride? We'll stick to the example I gave earlier. And I dump the sodium chloride into water and it all dissolves, right? Or at least up to a given saturation point. So here's my water. This would be the electronic breakdown of the water in terms of the dipole. What happens if I have sodium? Well, if sodium is no longer bound up to chloride, it's going to be Na plus in its electrolyte ionic form, a cation here. This plus is going to have a very strong attraction to the partial negative here when it's in solution. And that's how solvation works. Solvation is when you have an ion like this, and the ion is going to be surrounded by the polar opposite effect from what's called the solvent. So in this case, when we're dealing with water, water would align its partially negative oxygens with the sodium, which is positive. Now notice that sodium is not partially positive, it's fully positive. So now we're dealing with a partial charge and a full charge, and that's why this is the strongest of the bunch, because we're not just dealing with two partial charges anymore. So the ionic dipole, okay, is dealing with the sodium, okay, or in this case it's the sodium, but you're dealing with a formal charge, and then you also have a partial charge. Whereas the dipole-dipole, even the hydrogen bonding example, were two partial charges. It was a hydrogen and an oxygen in water, and they weren't these free-floating ionic forms. So you could also have the same thing with chlorine. The chlorines would align themselves with the hydrogens because the chlorines have a negative charge, so the hydrogens with their partial positive would give these stabilizing effects to the chlorines. These are by far the strongest intermolecular force. When you have ionic electrolytes that are hanging out and behaving this way with the solvents. All right, and just to clean this up, I'm going to put partials here. These oxygens are not fully negative, they're partially negative. It's the sodium that's got the formal charge here. Okay, and so this is what leads to dissolving. Okay, so the fancy word for this is solvation. Solvation refers to being able to dissolve a given ion in a given solvent. So in this case, we're talking about sodium chloride dissolving in water. Sodium chloride would be called the solute, and then the water would be called the solvent. And it's the intermolecular forces at play here that are allowing for this solubility to occur. So if I put sodium chloride into something like hexane that's not going to have this level of ionic ability to work with the hydrogen bonding, hexane only has London dispersion forces. It doesn't have these strong polar dipole forces like hydrogen bonding. And so I would not expect an appreciable amount of sodium chloride to dissolve in hexane. There's a terminology, like dissolves like, and that's where that comes from. You need to have like polarity or like charged behavior, like electronegativity, in order for things to be soluble or cooperate with one another in solution. So that really covers, right, the intermolecular forces topic in full. So what I'm going to do now is I'm going to go ahead and I'll clear the board. I will put up questions. You can try them and then we'll go over the answers. So give me just a second and we will bring the questions up. All right, everybody. So I have developed these questions and you should be able to answer all three of these based on the content that we just went over in the intermolecular forces lecture. So the first question here is, which molecule would not undergo hydrogen bonding? Now, when you take a look at this, remember that hydrogen bonding involves hydrogen bonds to either oxygen, nitrogen, or fluorine. Now, all four of these molecules have nitrogens or oxygens, so it's not going to be quite as easy as just ruling out one of them that doesn't contain that atom. You're really going to need to look at the structures and see which of them does not contain an oxygen or nitrogen that also has hydrogen bonds. Number two, which molecule would have the lowest boiling point? We've discussed the various effects of physical properties due to intermolecular forces. So if you take a look at those there, you're going to be comparing the intermolecular forces present in all of these compounds. And then number three, which of the following would not be affected by intermolecular forces? And you've got a couple that you can select from there, including boiling point, flammability, melting point, and surface tension. So go ahead and pause the lecture here. You want to try to answer these by yourself before you go through the answers with me. So pause the video and then I will see you in just a minute. All right, hopefully everybody had a chance to work on these. So let's go ahead and discuss the answers and why each answer is what it is. So I'm going to switch my ink to red here as we're going through these. First question, which molecule would not undergo hydrogen bonding? Well, hopefully everybody was able to easily eliminate water, because that was the example we were using throughout most of this lecture. Water is one of the iconic substances that will undergo hydrogen bonding, so that should have been an easy elimination. Now, what we also talked about were alcohols, and we did mention ethanol along with a few other examples. So this right here is methanol, and the OH bond in the alcohol means that methanol can undergo hydrogen bonding, so it would also be out in terms of the choices. Now this leaves C and D. If I take a look at C, C is a functional group known as an ether. And so you have a ethyl group, CH3CH2, an oxygen, and a methyl group. So the name of this ether, some people have heard of diethyl ether. The name of this ether would be ethyl methyl ether. However, the oxygen that's present here does not have any hydrogens directly associated with it. All of the hydrogens are associated with carbons. And so ethers do not have the ability to hydrogen bond, whereas NH3, ammonia gas, does have hydrogen bonding ability because the hydrogens are directly attached to a nitrogen. So even though there's an oxygen present here, and I might be able to get some dipole-dipole interactions, they are not going to be hydrogen bonding interactions. And this is very evident when you take a look at the boiling points of ethers. Ethers have relatively low boiling points, and they're very flammable solvents in comparison to things such as water. Alcohols are flammable, but they do have higher boiling points, so they tend to be a little bit safer when you use them. All right, number two, which molecule would have the lowest boiling point? So we have methane, hydrofluoric acid, ethanol, and propane. So of the bunch here, two of these hopefully were easier to eliminate than others, and the two that I'm looking for would be the hydrofluoric acid and the ethanol. And that's because both of these would undergo hydrogen bonding. As we just discussed in the question above, alcohols, and fluorine also falls into that category because of its electronegativity value. Those are both going to have hydrogen bonding present. And hydrogen bonding is a very high level intermolecular force. It's going to lead to high boiling points, not low boiling points. So that leaves methane and propane. Now methane and propane are very similar, except one group has slightly more carbons and hydrogens, but they are all hydrocarbon when you look at their general structure. So between methane and propane, it is the methane that's going to have the lower boiling point. Now both of these are still gases at room temperature, but the reason methane has the lower boiling point is that it has fewer London dispersion forces available than propane. So that is to say, the propane molecule has more bonds, and therefore it has more temporary dipoles that can occur throughout its general surface area. So more dispersion forces means a slightly higher boiling point than you're going to get with methane. So this would be the lowest, because remember we weren't asking for highest, we were asking for the lowest boiling point of the bunch. Now number 3, which of the following would not be affected by intermolecular forces? Again, two of these should have been easy grabs. We were talking about them very readily. Boiling point is out and melting point is out. In fact, the question above this was just talking about boiling point and was asking you to compare intermolecular forces and their effect on boiling point. So boiling point and melting point are both going to be affected by intermolecular forces. That leaves flammability and surface tension. So surface tension, if you think about if you were to lay a needle or a paper clip on top of a piece of water, and the reason it can float, whereas with other liquids it would sink, and then you can think about something that would have even more hydrogen bonding than water, it's going to be able to hold those compounds, whatever they are, even better. So some examples of this, you can also see those water strider bugs that will walk or glide across the top of water. It's the surface tension of water that's allowing that. Now, the question is, which of these two is not affected by the intermolecular forces? The surface tension is a physical property, and therefore it will be affected by intermolecular forces. The reason that liquids can have the surface tension that they do when you compare them to one another has to do with the forces found in between the liquid molecules. So that is an intermolecular property. Flammability, however, is inherent chemically to the substance. So it doesn't matter that alcohols have hydrogen bonding and ethers don't have hydrogen bonding. They are both flammable substances. The intermolecular forces did not play any role in that. It was the intramolecular forces, the internal bonds, and the fact that they have hydrocarbon bonds is what's leading to that flammability property. So this is, the key here is that flammability is a chemical property. It is not a physical property, and it is inherent to the substance itself and the bonds that make up that substance. It's not going to be related to any of the forces or attractive forces going on in between the molecules. Okay, so what I've done here, I've just cleared off the previous work, and I've brought up 3 additional questions that I want you guys to practice related to intermolecular forces. So here they are. Carbon dioxide is a gas at room temperature and will only form liquids at high pressures. So what would best describe the reason for carbon dioxide behaving this way? And you can see here there's several options. And note that IMF stands for intermolecular forces. Number 5 says which would be most soluble in water, and you have a few structures there. So keep in mind that we discussed like dissolves like, and I also want to point out here that while you're looking for similar intermolecular forces to that of water, you have to consider all of the intermolecular forces at play. And as you start to compile more of one type of intermolecular force than another, it can start to outweigh that other force. So what do I mean by this? I mean, if you have, for instance, an alcohol that has a very long hydrocarbon chain. So we were talking about octanol earlier in this series, or octane. the number of London dispersion forces and the amount of hydrophobic activity in that hydrocarbon portion is sort of going to outweigh or outbalance the hydrogen bonding occurring by the alcohol. That's not to say that the alcohol at the end of that 8-member chain wouldn't do any hydrogen bonding or participate in it. It's just not going to be nearly as effective at hydrogen bonding in comparison to all of the London dispersion surface forces that we would see there. So keep that in mind. The smaller, when you're dealing with those types of forces, usually the stronger the interaction. And then when we get to number 6, okay, it says acetone is best described as being capable of, and there's several options there that relate to intermolecular forces. Just so that everybody is aware, it's a fairly common structure, but acetone looks like this. So you have a methyl group on one side, a carbonyl group, and then you have a methyl group on another side. So acetone is one of the simplest, in fact it is the simplest ketone that you can come across. So that is the structure of acetone. Use that when you're trying to assess which answer would be correct here. So go ahead and pause the video, work on these, go back over the lecture again if you need to find specific points, and then we will practice these in just a second. Okay, so hopefully everybody had a chance to work on this. Let's discuss these. Number 4, carbon dioxide is a gas at room temperature and will only form liquids at high pressures. This is because CO2 is, and then we have several options here. So what I first want to do before we start attacking this problem is you should have the structure of carbon dioxide. Okay, now I did provide acetone because it's a little less commonly known. However, carbon dioxide, CO2, should be a structure that you're comfortable with. Okay, so this is carbon dioxide. If we were to take a look at the general electronegativity here, we would say that the carbon is partially positive and the oxygens would be partially negative as far as electronegativity is concerned. But what's key here is that there's going to be an equal and opposite pull because this structure is linear. So the pull is going to go in equal and opposite directions, meaning that there would be, just similar to a hydrogen-hydrogen bond or a fluorine-fluorine bond, you're not going to have any dipole moment or permanent dipole in this molecule because they cancel one another out in terms of their pulling ability on electrons. So, would we classify this as polar or nonpolar? Well, based on what we see here, even though there are polar bonds that have differences in electronegativity, the overall molecule, because of the equal and opposite pull, is going to be considered nonpolar. We would not see a dipole of any amount or significance when we are looking at this equal and opposite pulling. So if this is nonpolar, that gets rid of option A, because we said polar here, and option C, again, because we're calling it a polar molecule. We know that it's a nonpolar molecule. So then the question is, does it have weak or strong intermolecular forces? Well, it does not have any type of dipole moment that's permanent here. So it could not have dipole-dipole forces, and therefore hydrogen bonding, which is a form of that, could not exist. And what we're really left with is the weak dispersion forces. So the best option here is that CO2 is a nonpolar molecule with weak intermolecular forces. And that is helping to explain what we see up here. All right, so when we take a look at this, if something is a gas at room temperature, compare it to something like water with hydrogen bonding that's a liquid at room temperature, all right, this would be because of weak intermolecular forces. It doesn't take a whole lot to break apart these carbon dioxide molecules and get them into the gas phase. And at room temperature, carbon dioxide is a gas. You have to have very high pressures in order to make it a liquid at room temperature. All right, number 5, which would be most soluble in water? All right, so one of these should be obvious. First of all, let's state water would have hydrogen bonding. We know the structure of water here simply look like this. You have your lone pairs. Okay, we'd have hydrogen bonding available. So D should be the first one that you automatically cross out because this is just a hydrocarbon chain. Propane gas is not going to have anything other than some dispersion force. It's not really going to have any hydrogen bonding or any sort of dipole moment. So then when you come up, if you take a look at these others, you have methanol. That seems like a good candidate because it's an alcohol. We do have this OH group here. This right here, CH3OCH3, as stated in one of the earlier problems, is an ether. And while ethers have dipoles, okay, because of the oxygen here, and note that the flow of the dipole is going towards the oxygen and towards the oxygen in this case. They're not going away, so this isn't equal and opposite. They're converging on the same point. Okay. Now, this ether would not have hydrogen bonding capabilities, so it's probably not going to be the best candidate in terms of solubility with water, because again, we're looking for like dissolves like. And then you have another alcohol down here. This would be hexanol. Right? And if we're looking at hexanol, we have quite a large hydrocarbon chain, which is why I tried to warn you guys about this, because it was going to be a debate between the two alcohols. It turns out that this has a lot of London dispersion forces present, and because this gets so bulky, it starts to interfere with some of the hydrogen bonding that's going to occur with water. Methanol turns out to be the best candidate because of its relatively small size, which is somewhat similar to water. So methanol, ethanol, any of the smaller alcohols are going to be very soluble in water. And then number 6, acetone is best described as being capable of what? Well, if you take a look at this, and then you take a look at acetone over here, let's change colors just so that we're staying on track. We'll go with purple. Okay, so the acetone, the carbonyl has a partial positive on the carbon and a partial negative on this oxygen. So we definitely have a dipole that's headed in this general direction. So we can say that we have dipole-dipole forces. Okay. Do we have hydrogen bonding? Well, I don't see, even though I see an oxygen, I don't see an OH or an NH or an FH of any sort. Those are the three that involve hydrogen bonding. While there is an oxygen and there are hydrogens, there is no hydrogen-oxygen bond. And so we would not have hydrogen bonding present if we just had acetone molecules. Now, are there London dispersion forces here? This can be a little bit tricky, but the answer is yes. We do have London dispersion forces in this case because all molecules have London dispersion forces. There are still electrons moving back and forth when we're looking at the bonds involved in acetone. And so the best answer here, the correct answer, is D. Both A and B are correct. So you didn't want to select either of these individually. You really wanted the group pairing because everything should have London dispersion forces, and then we do have some dipole-dipole interaction based on the carbonyl, and that would be the answer for acetone. Alright, so hopefully this was useful in terms of addressing some questions and getting you to think a little bit about intermolecular forces. So let's bring up a summary table and just discuss the things that we went over in this lecture. And I will clear this off and bring that up in just a second here. Okay, so everybody should be able to see the summary table here that we now have up on the lecture. So we talked about intermolecular forces, and we defined those as forces that were between molecules. Now these forces are weaker than actual bonds themselves. So intramolecular forces are within the molecule itself. And that is going to be the actual bonds, the covalent bonds, the shared electrons. Those are going to be stronger relative to intermolecular forces. So hopefully you can see over here that I have a drawing of two water molecules involved in hydrogen bonding. And if you take a look, the red arrow pointing to the OH bond is referring to intramolecular forces, meaning the bond that is actually shared between the oxygen and the hydrogen. And then we also have intermolecular forces. This is between two water atoms, and specifically, if you're looking at this, it's represented by the dashed blue line here. We're talking about a partial positive hydrogen on one water interacting with a partial negative oxygen on the other. So that would be an intermolecular force. Like we said at the beginning, internet means between. So we have this sort of weave net between people. So if you think about intermolecular, it is between molecules. So we also discussed that as intermolecular forces increase, the physical properties have a tendency to increase. So keep in mind that this is a direct relationship. We see an increase in the IMFs. We see an increase or a tendency to elevate the physical properties. So boiling points become elevated, and we see melting points that are elevated. Viscosity is elevated. So things that have higher intermolecular force energy levels are going to pour at a slower rate. That's viscosity. It's going to have a slower time or an increased elevated pour rate in terms of the amount of time it takes. So we're looking at an increase in these properties. Now, the actual intermolecular forces themselves, even though we are looking at generally weaker forces, okay, let's move this down here. All right, so you've got these 4 intermolecular forces, and this is increasing in strength as we go down the table. So the weakest at the top are the London dispersion forces. And remember, these are due to temporary shifts in electron movement, and they form and dissipate very rapidly. So these are fleeting. They're not going to stay around for any long period of time. All molecules are going to have these, and that's because whenever we're dealing with a molecule, we're going to have at least 2 atoms that are sharing a set of electrons, even in the simplest of molecules, like hydrogen gas. Then we have dipole-dipole forces. These are permanent differences in the electron density. So what we were talking about with London dispersion forces, it's no longer a fleeting force. It's going to stay permanently in that dipole locked position. This will not dissipate, and this is due to differences in atom electronegativity that stays within the molecule. And so these are stronger because they're not going to dissipate the way that London dispersion forces would. Hydrogen bonding, remember, is just another type of dipole-dipole force, but it is the highest ranking of the bunch. So we're talking about very high energy that's required in order to start breaking apart molecules from one another at this point. This occurs with high gaps in electronegativity. In fact, you only achieve hydrogen bonding when you have oxygen-hydrogen bonds, nitrogen-hydrogen bonds, and fluorine-hydrogen bonds. Those are the 3 sets that are exclusive to hydrogen bonding. So if we had a hydrogen-bromine bond or a hydrogen-carbon bond, those would not be considered candidates for hydrogen bonding because they do not have a large enough difference in electronegativity. And then finally we talked about ionic dipole forces. These are very intense attractive forces of solutes or ions. We've also mentioned them as electrolytes with solvents, the liquids, and most of the cases that we've talked about we used water. This is responsible for the solubility of solids in liquids. So we talked about sodium chloride dissipating or dissolving, right, in the solvent. And it's the solvation or the alignment of these positive cations and negative anions with the opposite charge, the partial opposite charge of the solvent. And so ions will align with these partial charges, and that is an ionic dipole force. So hopefully this summary was able to succinctly bring everything together so that you could have a reminder of what we just talked about over the past lecture. So thank you very much for learning with us, and we will see you guys for the next lecture. Take care.